model the kinematic and dynamic of a mobile robot and how to design a simple controller happening in cars and mobile robots. The first one is a slip ratio, which is the normalized difference between the velocity of the wheel, which is calculated from its spinning velocity, and the actual velocity of the wheel center. It can be almost zero if the wheel is rolling perfectly, or it can be positive or negative depending on the acceleration or the deceleration of the robot. The other definition here is a slip angle, which is the direction mismatch between the direction that the wheel is heading with its steering angle and the direction that the wheel is actually going toward. You can see the relation here. Delta here is the steering angle, and the other one is the actual velocity of the center of mass of the robot, center of the wheel. With these two definitions, we can model the tire ground forces. One of the most famous models that does this is magic formula model that shows the relationship between the longitudinal force and slip ratio, as you can see here, or the relation between the lateral force and slip angle, as you can see here. As you can see, they both have some linear behavior and are proportional to some slip, and then they start saturating. A good controller should keep these forces in their linear region so that the slip doesn't get out of control. Now let's go to the kinematic modeling. This is a simplified bicycle model which is appropriate for our robot situation. As you can see here, these are the non-holonomic relations between the velocities of the center of mass of the robot and the velocities and the steering angles of the wheels, front and rear wheels. As you can see, this is the kinematic non-holonomic relation. Next, we can go to model the dynamic of our robot. As you can see, these are the same lateral and longitudinal forces that act on the robot, plus some other external forces, which are the air drag force and the projections of the gravity. If in the acceleration terms here in the left side, you can see it is composed of the derivative of the velocities and the rotation-induced terms. The longitudinal force here are the same forces from the modeling with the slip ratios, which we saw earlier. And the lateral force is a approximate linear form of that force with the slip angle, with some proportional coefficients here, which is CAI. For this control, I am going to simplify my dynamic model with the assumption that the robot has small steering angles, and that is only acceptable if the robot has smooth maneuvers and doesn't go on sharp turns and sharp maneuvers. The other thing here is that I have replaced the lateral force with its linear approximation with the proportional coefficients and slip angles. As you can see here, these are the proportional coefficients of the lateral force modeling, as you can see. And the term that calculates the slip angle, which we had here, is replaced in that simplified dynamic model. So the other thing that is important to model is the tire's own dynamic equations, which it's important because it relates the motor torques with the longitudinal forces here. Because as you know, our real input to the system is motor torques. This term here is the rolling resistance term, and Fz here is a vertical force, and Cr is rolling resistance coefficient. So let's go to design a simple nonlinear controller for this model. The kinematic controller, which is the outer layer, uses the position errors and the desired robot center of mass velocities. This is the kinematic Lyapunov-based control laws that is created, and these velocities will go and enter our inner dynamic controller as the references, and with some analyze on the Lyapunov function, we can prove that these control laws will guarantee that we have stability in the sense of Lyapunov. The dynamic controller, which is the inner layer, is a simple feedback linearization controller. As you can see, this is our nonlinear dynamic model, which we established before. And here the G matrix is numeric and invertible. So we can easily eliminate the nonlinear terms and design this controller here, this control law here. For the linearized model here, we design a simple state feedback control with equal gains of 10, and because this is a tracking problem, we have to add our desired accelerations in the linearized controller. And some other thing is that, as you can see in the equations of the dynamic model, our inputs to the system, that are the control outputs are the traction force and the steering angles of the front and rear wheels. Now, the only thing that is left, because our real input is the motor torques, but the output of this controller is the traction forces, we have to control the wheel dynamics to provide the required motor torque. We have three options. The first option is to ignore the wheel dynamics here and just use this term here, which is not accurate, but it would be computationally cheap. The other thing is to consider the wheel dynamics, which is here, and provide the reference desired wheel rotational velocity for it. The first option is to calculate that desired velocity with those kinematic equations we had before. And the third option, and the second option to provide that desired wheel rotational velocity is to use a slipover model, and with using that longitudinal force versus slip ratio model, like magic formula, we can calculate the desired slip ratio based on that traction force outputted from the controller. Here I have a more simple model for that force, which with the tangent inverse function, and with this modeling here, I can calculate the desired slip ratio from that desired traction force. Then, with the relationship of the slip ratio, I can calculate our desired wheel rotational velocity here. This is my designed controller block diagram. As you can see here, this is the kinematic controller, dynamic controller, the plant that the inputs are going to, and as above, we can provide our wheel motor torques to our system and to control it with that slip ratio equation and wheel force model. This is the designed controller in Simulink. And this is the resulted path following from this controller. As you can see, it goes from the supposed point that it has to start to follow that circular path. And this is the desired velocity tracking of the designed controller. As you know, the feedback linearization controller is very sensitive to accuracy of the model, and we have to use some accurate filters like extended Kalman filter for it to actually work.